We wouldn't get to today's modern technology, medicine, and research without yesterday's discoveries. And as nutrition students, what could help acquaint us more to our current field of study than learning about major nutrition discoveries from the past?
The first ever recorded discoveries on food nutrition were known as the Chemical Revolution in France. It all started with Claude Berthollet, who found that the vapor that came from decomposing animal matter was ammonia, and that this gas was composed of 3 volumes of hydrogen and 1 volume of nitrogen, or around 17% hydrogen and 83% nitrogen by weight. This was an impressive work considering the equipment available at the time. This was one of the discoveries that led to the assumption that nitrogen is necessary for humans to survive. However, this was opposed by Magendie's infamous experiment on dogs. He fed dogs with food that was accepted as nutritious but did not contain nitrogen such as sugar. The result was that the first dog continued to eat well for about 2 weeks and then began to lose weight and develop corneal ulcer, and then it died after a month. He repeated the experiment but tried using olive oil, gum, or butter for each dog. All produced the same result, but there was no ulceration found in dog that received olive oil. This showed that foods that did not contain nitrogen can still sustain life. This was an important experiment because it showed that an animal species could be used as a model for humans because our bodies were essentially similar to animals. This led to many more discoveries in the future using animals such as rats. Early discoveries regarding calorimetry were also found with the help of animals. In 1894, Max Rubner showed that a dog's heat output is equal to the heat of combustion of the food that it was metabolizing. More conclusive discoveries were found by Wilbur Atwater, who was able to build a respiration calorimeter, big enough to fit a human and house him or her for a long time in order to directly measure his or her heat output. It took Atwater and his group 5 years to fully test and build this machine. With it, they were able to precisely confirm that the heat produced by and within the human body is equal to the heat produced out of it. Unfortunately, Atwater was later disabled by a stroke, for which his equipment was taken away from his laboratory and was unaware that this group had already split up. Nevertheless, Atwater became widely known as the father of nutritional science in the U.S. through his research and major contributions to the USDA. In the 1850s, another important figure, Claude Bernard, discovered that the secretions in the small intestine from the pancreas, together with the emulsifying effect of the bile, were the major sites of digestion of fat into glycerol and free fatty acids and its absorption. The stomach was first thought of as the major site of digestion, but this study made focusing only on gastric digestion seem less important.
In 1746, a clinical trial was led by James Lind on sailors at sea for the problem of scurvy. He was able to observe that citrus fruit was a cure or preventive for this disease. Scurvy was also a problem in prison, but the only common factor found to explain the outbreaks was that before the outbreaks, potatoes were removed from the prisoners' diet for some time. But when they were added back, the disease disappeared. Citric fruits and potatoes were both rich in vitamin C, and this is important because now we know that scurvy is caused by a deficiency in vitamin C. During the 1880s, another disease was discovered to be caused by a nutrient deficiency. This illness, called beriberi, classified as a polyneuritis. It is characterized by weakness and numbness in the legs, and later heart failure and loss of breath. These symptoms were commonly found among sailors and native army troops. Multiple researchers initially attributed this disease to microorganisms. Professor Peckel Haring theorized that it was caused by an unusual bacterial infection. Other professionals who led parallel researches had similar early hypotheses. Christian Eichmann initially thought it to be caused by the development of microorganisms under favorable conditions caused by cooked white rice. Leonard Braddon thought it to be caused by pathogenic fungi growing on the porous surface of white rice. Contrary to their initial theories, a Japanese naval surgeon named Kanehiro Takaki, who had conducted the research regarding beriberi before them, believed that he had affirmed the cause of the disease, which is a deficiency in protein. He observed that the only difference between the Japanese sailors who have acquired beriberi and the European navies who had none was that the Japanese had a diet much lower in protein content. He was able to convince the authorities to switch the rations given to Japanese sailors, increasing the amount of food rich in protein. This change in diet produced fruitful results, as no deaths were recorded and there were only 14 cases of the disease. Further research held by the aforementioned researchers Eichmann and Braden also delivered similar results as of Takaki's, wherein they found that beriberi was a product of a deficiency rather than an intoxication. Similarly, rickets, which is characterized by a lack of calcification in the bones and leg and rib deformities among children, was also found to be caused by a sort of insufficiency. After collective research, Walter Cheadle found that the children who had this disease were mostly not breastfed and were fed with inadequate substitutes. Furthermore, Theobald Palm, a medical missionary in Japan, found that there was a complete absence of rickets in the country he currently resided in. He concluded, along with information he gathered from fellow missionaries, that rickets did not occur among people who were constantly exposed to sunlight. In conclusion, a deficient diet for children, especially the lack of breastfeeding, and an insufficient exposure to sunlight were found to be the major causes of rickets during this time. Regarding how experiments should be practiced, the researches conducted regarding anemia amplified the significance of performing precise and impartial analytical procedures. Anemia was a common problem among teenage women around the 1800s. It was described as having a lower blood cell count and an even lower hemoglobin level, and was generally accepted to respond to an administration of ferrous sulfate. There was an assumption that the typical human diet had large amounts of iron. The physician Ralph Stockman investigated further on this assumption. He found that there was an inaccuracy in the method of iron measurement during that time. The standard procedure also measured carbohydrates as iron unknowingly. Hence, bread was considered to contain as much iron as meat. Using his own method, he found that the anemic women only consumed a daily intake of 3 milligrams of iron. Through his more accurate procedures, he was able to conclude that the losses during menstrual cycle and the low intake of iron was the cause of anemia among young women.
Biochemist Casimir Funk had parallel results regarding the previously mentioned rickets, pellagra, and scurvy, for which he concluded that they were deficiencies but of unknown factors. He also proceeded to coin the term vitamins or vital amines to refer to these factors in 1912. Letter E was omitted after it was realized that they could not all be amines, thus marked the beginning of the vitamin era. The idea of experimenting using purified diets or mixtures that only contain the purest form of proteins, carbohydrates, fats, and minerals was the most widely used practice to associate a diet with a particular disease. Gowland Hopkins, a professor of biochemistry at Cambridge University, was the first one to associate deficiencies of a purified diet with human diseases. Based on his studies on mice in 1906 to 1907, he concluded that no animal can live upon a mixture of pure protein, fat, and carbohydrate. His idea was similar to that of Cornelis Beckelharing, the leader of the Beriberi Commission in Indonesia, who reported that mice would not grow on diet of casein, egg albumin, rice flour, and minerals. E.V. McCollum and his colleagues reported that the rats they were experimenting on needed a fat-soluble factor A and a water-soluble factor B. In 1908, a group from a medical school reported that puppies fed bread or oatmeal developed rickets when kept indoors. It was then concluded that inadequate fresh air and exercise may result in the development of rickets. One favored treatment for rickets was exposing an infant to sunlight or ultraviolet lamps. In 1924, it was discovered that food irradiation was another effective way to prevent rickets. Apparently, irradiation activates a factor, and this factor was called the vitamin D in 1931. Joseph Goldberger, the person in charge of the Public Health Service pellagra program, believed that pellagra was not infectious. He went to state that unbalanced diet was the root of the said disease. To prove his idea, he experimented on volunteer prisoners by feeding them a diet that might induce pellagra. 5 months to the experiment, his volunteers started showing signs of dermatitis. In another study, he concluded that pellagra is caused by an infectious agent. Finally, in 1937, nicotinic acid and nicotinic amide, now called niacin or the vitamin B3, were found to cure pellagrous patients. The experiment that led to the concept of vitamin A as a fat-soluble vitamin necessary in supporting growth and preventing serophthalmia in rats proved to be relevant when a group of children accidentally developed serophthalmia during the World War I. Karl Bloch, the pediatrician in charge, prescribed them to take cod liver oil. As a result, the eyes of the affected group cleared up and they began to grow faster. Additionally, carotene was discovered to be the precursor of this vitamin. Vitamin E or tocopherol became a popular treatment for abortion and forms of muscular dystrophy. The discovery of this vitamin also paved the way for the discovery of another essential factor, the vitamin K, which was recognized for its role in blood coagulation and hemorrhaging. The vitamin era also introduced the concept of essential amino acids. Essential amino acids are those that cannot be synthesized by the body, thus should be provided in the diet.
In 1944, it was discovered that folic acid prevents macrocytic anemia in monkeys and chickens. This type of anemia is characterized by red blood cells being larger than their normal size. Folic acid can also be used as a growth factor for some bacteria. Further research proved that other bacteria can also synthesize this vitamin. In 1946, Robert Stokestad and his colleagues at Landerla Laboratories identified the then unknown substance as N,6-tyrrhenyl methyl P-aminobenzoic acid conjugated with one or more L-glutamic acid residues, which can be simplified as terone mono or polyglutamate. Upon absorption, its reduced form is tetrahydrofolic acid. Large doses of this substance administered by mouth or injection is used to treat people with pernicious anemia by its ability to stimulate red blood cell production. However, in 1948, it was discovered that patients treated this way showed neurological disturbances that responded to liver extracts. It was also discovered that folic acid also responds to leukopenia, a disease characterized by a deficiency in white blood cells. Folic acid was also proved to be important to the development and nourishment of babies. It was observed that a large number of mothers with babies born with neural tube defects seem to have come from lower income groups, and the suspected causes are the high level of potato consumption and the fact that only few of the mothers had been taking vitamin supplements before or during pregnancy. Neural tube defects occur within the first 21 days of pregnancy, which makes nutrition a crucial step because some mothers discover about their pregnancy later. A trial involving pregnant women was conducted. Before conception, they were given supplements that contained folic acid, which showed that the incidence of malformed embryos was higher in those who did not take the supplements. In response to this, bread flour were enriched with folic acid. High folic acid in adults reduces the level of homocysteine in the bloodstream, which effectively lowers the risk of heart disease.